if you're not very familiar with XFlow, remember you've got a project tree, graphic view, function viewers, and the workflow is pretty simple from left to right. So let's get started with that example, which is actually the Rushton turbine we've seen in the previous case in the presentation. So first of all, let me just import maybe two geometries that will be my for my simulation today. First is one tank, which is the tank with the baffles, and on the other side is the rotor of the geometry. So that is going to be my, let's say, domain of simulation, and that is going to be my mixer. So let's get started from the order. Here you can see this is a 3D simulation, and you've got different flow models. So here we're not going to work in single phase, but instead we're going to do a free surface simulation, since we've got indeed a free surface in that case. You can see there is a domain outside because we're still in a nice analysis type that is external, but we've switched into internal because in that case we want to model, let's say, the boundary of the domain as being this geometry here with baffles, that cylinder with baffle. And here the simulation will be isothermal. I just skip the rest because it's not relevant for that simulation. You can see when we switch to free surface, we've got automatically gravity set as minus 9.81. So I'm going to leave that because my gravity will indeed be in y direction. I will just leave initially fluid at rest, so no pressure, no velocity at all, and just want to see how it starts rotating, starts mixing that up. The new thing in initialization for free surface flows will be the liquid region. You have to say, where is my liquid initially in my domain? Do I have everything filled with liquids, nothing filled with liquid, just some part filled with liquid? I can just define that through a function. So in that case, we're going to take a height of, for instance, 0.57 meter, and that low y is less than 0.57 meter, means that my liquid is going to be, it's a Boolean function, is going to be in that areas. So actually my 0.57 is something around here, okay? So let's say we are gonna fill that tank this way, and it's just enough, nothing else to do. When I switch to materials, then I've got the materials of density, temperature, viscosity, and so on. In that case, that's by default water because I switched to free surface flows, which is the most common, let's say, material for free surface applications. So I'm just going to leave that with default water properties. Okay, now geometries. You've got the two geometries. One is a tank, and the other one is the rotor. So remember, since XFlow is actually, well, sort of meshless, or you don't have to do any meshing at any kind, you know, so you just have to define your surfaces and your geometries correctly so that you can define where is my region of fluid and where is not. So we do that through the visualization of the normals. So you can see, for instance, I can see that tank, I can see inside it, because not because there is no surface in front of me, but because we've got something called backface cooling. That would be like this. If I disable it, it means I'm seeing my geometry just as is. Now if I enable backface cooling, I see through the surfaces that are pointing with normals towards the other way. So basically I can only see the normals pointing towards me, which means the other one from the other side. If I just reverse that orientation, you see everything is pointing outwards, and therefore I see nothing inside. That means my simulation is not going to happen inside that volume. If I reverse that, I can see inside. That means my simulation is going to happen in that volume. Just as intuitive as that, okay? For the impeller, just everything is pointing out. You can see the difference here, where you could see, for example, inside that geometry, but you don't want that. So you just keep the orientation towards the outlet and just keep that like this way. And now we've got defined, let's say, our volume of fluid being inside this and outside there. I can just define my motion of rotor. The only thing I have to do is switch from fixed to enforced and define a law where we prescribe the rotation speed. So in that example, I'm going to give minus 500, or well, actually the sign doesn't really matter because that turbine is just symmetric. So just 500 RPM, so that could be 360 degrees per second, and times t, which is a temporal variable. So that means I've got a 500 RPM rotation here induced, and what you can see now, I'm going to modify that frequency, but if you watch the timeline, now I can see my geometry is rotating, and I can see everything is fine. So you can see my local axis also indicates, okay, I'm rotating around my y-axis, everything is fine, this is rotating, we are good, and defining a moving geometry is as simple as that in XFlow. We can just switch then to the simulation parameters, and here we define time and resolutions and these kind of things. So in that case, I'm going to define a 5-second simulation, which is enough to give a few rotations to mix my simulation, my fluid in that simulation. I could use different refinements and so on, but I'm going to keep a 5mm resolution uniform in that domain, just to make it simpler, and a couple of different parameters about how much data you want to save. And this is it. You just have to run that. You just click Run, Start Computation, and the job starts. I've got that simulation run already, so what I'm going to do is I'm going to switch now to, well, the preloaded simulation so that we don't have to wait for the job to run. And you can see here, now we can check a couple of things. So let's create, for example, a cutting plane. You see, I just click that icon and I get a section of my domain. So what you have here is the velocity by default. I've got some controls in that cutting plane where I can just play and show different fields, pressure, but also vorticity and other types of domain as well. So when you see the velocity here, it's actually showing higher velocities on the outlet, on the blade tip, and is sort of propelling out in the radial direction the flow here. And you can see all the mixing as well here. We've got the voxelization due to the lattice structure that you can smoother using interpolation as well, which is basically just interpolating data. This is due to the lattice resolution in that case, which you can see also you can plot with the domain structure and see the distance between two lattice points in that case. So for this, we could check, for example, for a couple of criteria to see the convergence of the case. One would be, for instance, the kinetic energy to see the convergence of the case. And you can see, for example, that this is converging after some time, after 2 or 3 seconds, our kinetic energy is converging, which means probably our mixing is close to the end. Then we could also be interested in the rotor in different aspects. One would be, for instance, the moments applied by the liquid on that rotor, and you could also get, well, that curve here that you can see is actually converging very quickly in that case because the forces converges very quickly. The mixing is longer to establish because you've got a larger volume to establish here. So about 9-10 Newton meter. And a couple of different things. For instance, showing the interface of your flow with markers that you can see are representing actually the surface, the free surface of the flow, but also, for instance, with an isosurface, but can also be used to represent the flow. And finally, gives us, well, the video you've seen previously during the presentation, which is the mixing you've got here, exactly here. So you can see really the spiral of velocity induced and then raising up the fluid and liquid in that level, and on the contrary, the other side is quite low. Same thing here, level is quite high on the right side, but on the left side it's quite low because it's rotating, clockwise.